All right, so let's start with this. Any questions that came up in the groups or from you looking through the voice threads that you still have questions on that we should address? Abby and then Erica.
In terms of a cofactor versus the coenzyme, what do you want us to know?
Yeah, what is the big difference between the two of them? So a cofactor is inorganic. Usually it's a metal ion. So common ones would be that you would find are zinc, magnesium, iron are kind of the big three. And then a coenzyme is going to be an organic cofactor. And typically the main two that I think everybody is largely familiar with, NAD plus and FAD. Anorganic. Oh, sorry. So what did I say? Yes, it's anorganic. Yes.
Not inorganic.
No. Aorganic. I'll use improper English. Yeah, basically coenzymes are, you can kind of think of it as cofactors are the larger group, and then coenzymes are a subset of that. Okay, so they're included within it. What is the big role of these coenzymes or cofactors? What's that? Oh, sorry. I heard somebody mumbling. I didn't know if it was about that. We're good? Okay. They can. They can help a bit with the, do you mean like shape of the enzyme? A little bit. That's definitely true. What else? They're typically involved at the active site, so that means that they're in some ways involved in the reaction. They themselves are part of the catalysis. And usually the role of these coenzymes and cofactors, in the case of the cofactors in case of the coenzymes NAD and FAD, they're involved in redox reactions. They'll be involved in accepting electrons or giving away electrons in redox reactions. What enzyme class is involved in those redox reactions? Of the three that I'm asking you to know. Yeah, dehydrogenases are the major ones involved in redox reactions. So if you see an NAD or an FAD in a reaction, you can start to do some word association here. If you see that, a dehydrogenase has to be involved. Okay, we'll come back to that. Some cofactors like magnesium, iron, some of them are also involved in redox reactions. In particular, the electron transport chain, those complexes within the electron transport chain that we'll talk about on Wednesday, they have iron. And the iron there is to collect electrons and then hand it off to the next molecule in the complex. Other times, these cofactors are there to just stabilize the substrate in some way. So if the substrate, for example, produces a negative charge at some point during the enzymatic reaction, those positively charged cations will help to hold on to the substrate in the active site. So there's a number of different roles, but mainly it's for stability of the substrate and then involved in transferring electrons. Erica. You had a question at some point, right?
It was the same.
It was the same one. Okay. Okay, great. So dehydrogenase involved in redox reactions. And in biological redox reactions, there's two things that move. Obviously, chemistry will teach us that electrons move in redox reactions. You can use the mnemonics Leo says GER, or some people use oil rig. Right? Gain of electrons is reduction, loss of electrons is oxidation. But in biological redox reactions, it's not only electrons that move. What else moves? Great. What's that? Protons, hydrogen ions, exactly. And the name dehydrogen or dehydrogenase comes from removal of hydrogens. And so these dehydrogenases are not only moving electrons, but they're moving hydrogen ions with them. Okay, so that's a couple of key characteristics there that, again, we can associate. Other questions? Devin.
So dehydrogenase, is that the actual enzyme or a coenzyme?
That's the actual enzyme. And then the coenzyme it would be the NAD or the FAD. Okay. So ACE, ASE at the end usually is an indicator of an enzyme. And we're talking about three major ones: the dehydrogenases, the isomerases, and the kinases. What do isomerases do? Or what kind of reactions, Derek?
Isomerase changes the molecular arrangement of a molecule to a different formation.
Good. So same molecular formula, different structure, right? Basically, it creates isomers, another chemical term. What do kinases do? Mike?
The transfers phosphates from one molecules.
And this is the key point here. I want to hit on this, that what you said was it transfers phosphates from one to another. Sometimes, and most often, we're going to think of this transfer as being from ATP to some other molecule gaining that phosphate. For example, first step of glycolysis is glucose to glucose 6-phosphate, and ATP transfers a phosphate onto that glucose. But I want to point out here that kinases will work in the opposite direction as well. So later on in glycolysis, if you take a look at that worksheet, for example, last step, phosphoenol pyruvate to pyruvate involves another kinase enzyme. And in this case, the high energy molecule is that PEP, or that phosphoenol pyruvate. And as that phosphate gets transferred to the ADP to form ATP, that's another kinase reaction. Okay? The key point here is that kinases are involved in transferring between two substrates. This is in opposition to, some of you may have heard of phosphatases, which we say removes a phosphate. Really, it's not only that it removes a phosphate, but that phosphate's lost to solution. In the cases of kinases, it's always just a transfer from one substrate to another to create two new products. Okay? And we'll keep working on that. I wanted to point out this enzyme structure real quick, and the reason why I wanted to point this out was to make a comment on inhibitors real quick. So I think everyone's in agreement. Where do those competitive inhibitors bind? Bind the active site. And what has to be true then about the inhibitor and its relationship to the substrate? They look same shapes, similar identity. A lot of antibiotics are basically competitive inhibitors. They look like the natural substrate for enzymes. We briefly brought up penicillin about a week ago, discussing its role as a inhibitor of cell wall formation. It binds to a class of proteins, and we'll talk about this much later, but it looks a lot like the substrate for those proteins. So similar structure, but unable to actually for the enzyme to act on it. Where do non-competitive inhibitors bind? So what's the name of the... What's that? Basically, yes. Anywhere else, right? So a non-competitive inhibitor, one of the terms we can use is we say that it binds to an allosteric site. And in this image here, if I'm not mistaken, this is representing that allosteric site. An allosteric site, it's really hard to define what it is, because it's not like you can point to a protein and say, there's the allosteric site. An allosteric site is anywhere else on the protein or the enzyme other than the active site where a molecule can bind and therefore change the activity of the enzyme. And typically what they do is they change accessibility to the active site. So for example, let's say this is an enzyme here. And in this case, here is the active site, and a substrate can not only get in, but bind it very well. If we have a non-competitive inhibitor that binds to this, A non-competitive inhibitor might change the shape of the protein in a way to actually close that active site and now make it inaccessible to that substrate. So this would be a non-competitive inhibitor, or allosteric inhibitor, we might call it as well. Same thing. Activators, on the other hand, take closed active sites and open them up in order for the enzyme to now perform an activity. Classic example are cyclins and cyclin-dependent kinases. But in those examples, what we have is an enzyme, again, where that active site is kind of, oh goodness, now I'm just drawing crap. Oh, that's not good. I'll just stick to my circles. Where the active site is typically closed. Now when that allosteric molecule binds to it, it opens up that active site, allowing for that substrate to get in. So enzymes can be controlled in both of these formats, and those allosteric sites don't have to be the same site for both the inhibitor and the activator. In fact, some enzymes have both allosteric inhibitors and activators that can work on it at the same time. It's just a matter of metabolic flux, basically how much or what's the concentration of these different inhibitors and activators within a cell that ultimately determine how quickly does that enzyme work. Classic example of this is this one here, phosphofructokinase. Third step of glycolysis, kinase implies what? Yeah, transferring a phosphate, right? And in this case, it's transferring from glucose 6, or transfers from ATP onto fructose 6-phosphate to form one with 2 phosphates on it. Okay. This kinase is regulated both positively and negatively based on different types of products. So, for example, if this is a step of glycolysis, and we often talk about what is the role of glycolysis? What is the cell trying to achieve with it? Typically, the goal is produce energy, right? And energy we typically talk about in what form? ATP. So if there's a lot of ATP in the cell, a cell then will choose, quote unquote, choose to basically turn down the rate of glycolysis, slow down how much glucose is being burned, store it for a period of time when the amount of ATP within the cell is low. And so you'll see here in this example, phosphofructokinase, what this is showing is that ATP is actually an allosteric inhibitor. It will bind to somewhere other than the active site on phosphofructokinase, change the shape of that active site so that it can't bind to its substrate, and therefore blocks that step of glycolysis or slows it down so that the cell can not burn the ATP here to continue to drive glycolysis. So that fructose 6-phosphate essentially will get stored as a way to create an energy store for later periods of time. Citrate is another inhibitor. Where do we see citrate? Do we see it in glycolysis, Krebs cycle, citric acid cycle, or electron transport chain? Citric acid cycle, it's in the name, right? Also known as tricarboxylic acid cycle, or also known as Krebs cycle. So citrate is actually the first product that's formed within the Krebs cycle. Again, if that's high, that means ultimately the cell is committing itself to some form of respiration, either aerobic or anaerobic. And we know that that produces a boatload of ATP. So if citrate is high, the cell slows down these steps of glycolysis to allow for that energy to be produced, and knowing that citrate is going to lead to a boatload of energy at some point down the road. Now, on the other hand, AMP Adenosine monophosphate, basically what happens here, ATP would release a phosphate for energy to form ADP. ADP would release a phosphate for energy to form AMP. AMP represents a low energy state of the cell then. And so in order to ramp up the process here, AMP is an allosteric activator. It opens up that active site. It allows for it to be more accessible to the substrate fructose 6-phosphate, and therefore increases the rate of glycolysis to provide energy for the cell. Okay. So we see this time and time again, and not only in prokaryotes but eukaryotes as well, where we have activators and inhibitors that are really regulating how fast does an enzyme work. And each of these here, the AMP, the ATP, and the citrate, each of them binds to a different allosteric site on that enzyme PFK. Okay. Other questions? Questions on this topic of allostery regulation? Okay. What I want to spend some time now doing is actually practicing identifying. So that's what this worksheet is for. So this worksheet is one where on the front you've got an image of glycolysis. I don't list the enzymes or anything. I'm not even listing for you the name of the different molecules that are produced. Instead, what I've got are a series of questions. Fill in the blank, single word answer, phrase answer. And what you need to be able to do here is, the goal of this is really to get you to start identifying different types of reactions. So can you, from glycolysis, identify a kinase reaction? Can you identify a dehydrogenase reaction or an isomerization? Can you identify what we call a substrate level phosphorylation, which is essentially the type of reaction that a kinase drives? Substrate level phosphorylation means that a substrate is being phosphorylated, and we talk about in glycolysis in the Krebs cycle how substrate level phosphorylations will yield some ATP. And we'll contrast that on Wednesday to oxidative phosphorylation, which is the process by which ATP is formed during electron transport. Okay. So take some time to do this. We're going to work for about 15 minutes or so, and then we'll spend some time kind of reporting out here. At the very end of this, the last page kind of has like an overview of glycolysis, like how much ATP is produced, how much NADH is produced, blah, blah, blah. But then there are a couple of redox reactions. And what I want you to start to get familiar with, I haven't really talked about this too much today, but I do know that this is in the slides. I want you to get familiar with the following terms. Oxidized product, and reduced product. So in other words, which one has lost the electrons or gained electrons? And then oxidizing reagent, or oxidizing substrate, you could call it as well, and reducing agent. So those terms there imply the oxidizing agent is the one that is going to be taking the electrons. The reducing agent is the one that's going to be giving out electrons. And always we find these paired. That an oxidizing agent will become a reduced product at the end of a reaction, where a reducing agent will become an oxidized product at the end of a reaction. So practice with those terms and try to identify those from the reactions, given where you see hydrogens or electrons moving. So we'll work until about 8:42 or so, and then we'll spend a few minutes discussing and finish up for today. All right, go ahead. However, I put this worksheet together last semester, and the reason why I like it is because actually for part of the exam in the past, what I've done is put up pictures of glycolysis or other reactions and basically said, tell me what kind of what enzyme is involved, or if I say, hey, a kinase is involved, what's missing from this reaction? So it's starting to be able to identify, kind of doing some word association with those different terms. Dehydrogenases and NADH. Kinases and what else? What are kinases associated with? So what kind of reactions? Phosphorylations, which means what? We'd probably see ATP, ADP either being formed or used. So let's go through real quick, and I'm not going to go through the questions directly on here. I will put together a key for it if you'd like me to. I will work on that. I'll get it up. Try to have it by the end of the day for you to just kind of check your answers on. And if you have questions about it, let me know. But let's identify our reactions that would involve a kinase. So where are they? And you can just yell out the numbers of steps if you want to. 1, perfect, great start. Oh, shoot, 3, yes. So this one, yep. This one. I heard somebody say 7, yep. 10, yeah, right here. What's different between the 1 and 3 and 7 and 10? That's true. We do see that in 7 and 10. So this is, you may remember in glycolysis, we have this step in which the fructose 1,6-bisphosphates, it gets cut into 2 molecules and everything occurs in duplicate after that. That is definitely one difference.
They're opposite. ATP is being utilized in steps 1 and 3.
Good. Good. So in the first 2, those are we oftentimes think of those as energy consumption steps. And you'll notice here on the side it says stage 1. That's where we have ATP as an input. And then stage 2 is we start to get a little bit of payoff. We get ATP as an output. 7 and 10 are what we would typically describe as substrate level phosphorylations. And what we mean by that is that the ADP is gaining a phosphate to form ATP. So there are a couple of ways in metabolism in which we can produce ATP. Substrate level phosphorylation, transfer of a phosphate from one substrate to another, is one of those mechanisms, as opposed to oxidative phosphorylation, which again we'll talk about on Wednesday. Okay. How many ATP in total do we form? And I'm meaning here net total. Just 2, right? We put 2 in the first and third steps. We get 2 out in step 7. We get 2 out in step 10. 4 minus 2, 2. Okay. So 2 ATP total. Let me pause there. Any questions with the kinases? Okay. Where do we see redox reactions? Meg. Okay, so you're saying step 6. What are you using as your indicator that it's a kinase, or sorry, that it's a redox reaction? Good. So we have 2 NAD here. That's an electron acceptor. Get reduced to form NADH, and that is definitely an indicator of a redox reaction. Again, NAD plus and FAD are 2 of our major electron acceptors in redox reactions. What kind of enzyme would be involved? Perfect, dehydrogenase. Anywhere else where there's it's not really apparent in here. There is one more location where this happens. Typically we talk about glycolysis ending at pyruvate. We'll talk about fermentation on Friday. There's another redox reaction that occurs in fermentation. And that's just a side note. If you don't remember that at the end of today, we'll come back to it on Friday. All right. And then isomerization reactions. These are harder to identify unless you've got maybe the molecular formula. Derek? So step 5 definitely is one of those spots. This is where we get the conversion of one of these 3 carbon molecules into the other, definitely. One other spot where there's one is step 2. Glucose 6-phosphate to fructose 6-phosphate. Again, what's the key feature with isomerization reactions? Same what? Same formula, different structure. Okay? Oftentimes involves breaking a bond and then creating a new bond in return. I think we'll stop there for today. I don't want to go any further with this, but what I will do is kind of recap today the major points we were focused on. I'm going to go back to the objectives for this because I think that's a great spot to start off. Okay, so describe the structure and function of enzymes and their regulators. We've gone over terms like active site, substrate, non-competitive inhibitors, allosteric activators as ones that increase enzymatic activity. Darn you. And then identifying flow of electrons. We talked about redox reactions some. I want to make sure that we keep practicing with that. Especially on Wednesday. Electron transport chain is just chock full of redox reactions over and over and over again. So we'll watch that flow of electrons to model that. Again, another really big point here, make sure that you start trying to connect those different terms together. Dehydrogenases with NADH and redox. Kinases with ATP and phosphorylation, so on and so forth. Any last minute questions? All right, nice work today. I will see you all tomorrow in lab. Don't forget your homework coming to lab tomorrow.